Welcome to the Deep Dive. We're here to unlock some fascinating currents of knowledge, bringing you insights that, well, hopefully inform, maybe provoke a little thought, and perhaps even astound you along the way.
That's the plan.
And today we're doing just that by stepping back in time. Way back, actually, to an era that was absolutely buzzing with these audacious dreams of intelligent machines.
It's almost hard to picture now, isn't it?
It really is. I mean, think about it. The whole concept of creating artificial minds, it's fueled human imagination for, well, millennia. You've got ancient myths, automatons, right up to modern sci-fi.
Yeah, it's a deep-seated fascination.
But when did this grand, almost mythical dream really get its scientific footing? When did it move from story to lab? And maybe more importantly, what happened when that soaring ambition, that feeling that anything's possible, first collided with the, let's be honest, gritty reality of actually building these things?
That collision point is absolutely crucial. Because those initial moments, that kind of fertile ground where the field of artificial intelligence was really born, it set the stage for pretty much everything we see in AI today.
So we're talking about the pioneers.
Exactly. We're going to explore the bold, almost boundless optimism that defined those early pioneers. I mean, many of them genuinely believed that human-level intelligence in machines wasn't some distant future thing. It was just around the corner, maybe even just a few years away in their minds.
Which is just incredible to think about now. But what's equally fascinating, I think, is that right alongside that incredible optimism, you started seeing these currents of subtle yet really profound doubts emerge.
Yeah.
Almost immediately.
Right, not just technical snags.
No, exactly. These were fundamental questions, especially around the inherent complexities of things like natural language.
Yeah.
How we understand each other, or human vision, or even just the basic nature of learning itself. Doubts that honestly still echo in our conversations about AI today, wouldn't you say?
Oh, absolutely. They're still very much with us. So our mission today is really to take that deep dive into what many consider the definitive birth of AI, that pivotal 1956 Dartmouth conference.
Okay.
We want to uncover how those early dreams not only inspired just incredible innovation, fueling decades of research, but also, maybe inadvertently, laid the groundwork for these cycles of hype and, well, disillusionment that continue to shape the field even now. It's about understanding the sort of DNA of this technology.
Got it. So understand the roots to understand the present. And how are we tackling this? What sources are we drawing on?
Well, to guide us, we've gathered a pretty rich stack of sources. We're looking at foundational academic texts. Think Norvig and Russell, the kind of standard works. We've got historical accounts trying to capture the unique feeling of the time.
The zeitgeist.
Exactly. And also critical analyses, things like AI Snake Oil by Arvind Narayanan and Sayash Kapoor, which offer a more challenging look. So it's a mix, promises, challenges, the full picture, hopefully unvarnished.
Excellent. So we get the history, but also the critical context.
Right. It's not just recounting history. It's about digging into those foundational assumptions, those early psychological impacts that are still playing out in our, very AI-infused world today.
Okay, sounds like a plan. Let's unpack this fascinating history then. Let's jump right into that spark that ignited this entirely new field. Okay, let's really try and set the scene for you. Picture this. It's the summer of 1956. This isn't a summer of, social media buzz or streaming services. It's still relatively fresh from World War II.
A very different world.
Totally different. Computers were these massive room-sized machines. The very idea of a thinking machine probably felt like pure science fiction to most people, or maybe a dream for the distant future.
Something abstract, theoretical.
Exactly. And yet here you have this group of brilliant, incredibly ambitious minds gathered at Dartmouth College in Hanover, New Hampshire for a workshop.
And this wasn't just, another academic get-together with it. This was really a watershed moment, a genuine genesis point.
How so? What made it different?
Well, before this gathering, researchers were certainly working on similar concepts. You had early computing machines, people exploring cybernetics, or delving into what they often called complex information processing.
Right. Different labels, different silos maybe.
Exactly. There wasn't really a unified field, no shared banner to bring all these disparate efforts together. It was fragmented.
Okay. So Dartmouth brought them together physically, but also conceptually.
That's the key. It was here at Dartmouth that this new burgeoning area of research got its official name. The term artificial intelligence was coined right there.
Wow. Just like that.
Pretty much. And that phrase, in hindsight, proved to be just incredibly impactful.
So what was the thinking? Why artificial intelligence, and how did it land at the time?
Well, as some of our sources really keenly observe, coining artificial intelligence at Dartmouth turned out to be, and this is a quote, one of the most successful marketing terms of all time.
Marketing. That's interesting, not just descriptive.
Well, it was descriptive, but it was also more than just a label. It was this powerful conceptual leap. This new name, artificial intelligence, it instantly anthropomorphized machines and the collective consciousness. It made people think of thinking, learning, understanding, maybe even self-awareness.
Right, it sounds human-like.
Precisely. Attributes that, frankly, sometimes lent these machines, again quoting, more capability than they deserve in the popular imagination right from the start. It shifted the conversation away from just calculation or computation towards something much grander, much more, well, human.
That's a really fascinating point about the marketing power of a name. It sounds like they weren't just naming a field, they were essentially selling a vision, a promise.
You could definitely see it that way.
And the goals they laid out at Dartmouth certainly reflected that huge ambition. The workshop's explicit aim was, I think the phrase was, pulling together ideas about thinking machines.
Yep, that was it.
And you get this sense from the historical accounts of this palpable, almost infectious optimism, like human-level AI was just around the corner. It wasn't a question of if, but when. And for many of them, that when felt incredibly, tantalizingly close. Like, soon.
They genuinely believed they were on the cusp,
Yeah.
on the verge of creating something akin to a digital mind, or at the very least, reverse engineering human cognition within maybe a few decades. It was bold.
Hugely bold. But this ambition, it didn't just appear out of thin air, right? It must have built on earlier ideas.
Oh, absolutely. It built upon several foundational visions, intellectual currents that had been setting the stage for years. Perhaps the most pivotal, looking back, was Alan Turing's groundbreaking 1950 paper, Computing Machinery and Intelligence.
Turing, the father of computer science in many ways.
Indeed. And in that paper, he famously posed one of science's most profound questions. Can machines think? But crucially, this wasn't just armchair philosophy destined for the ivory tower. It was a radical call to empirical testability. He was essentially saying, okay, let's stop arguing about definitions and actually find out.
And his way of finding out was the Turing test.
Exactly. The now legendary Turing test, or as he originally called it, the imitation game.
For anyone listening who might not be super familiar, can you just quickly sketch out how that game was supposed to work?
Sure, Turing proposed this really ingenious setup. You'd have a human judge conversing via text. He called it a teleprinter, of course, not instant messaging back then, with two unseen entities.
Okay.
One of those entities was a human, the other was an AI program. The AI's explicit goal, to trick the judge into believing it was the human.
So fool the judge.
Right. If, after a set amount of time, the judge couldn't reliably tell the machine apart from the human, then the AI would be deemed to have passed the test. It basically focused on conversational indistinguishability as a kind of proxy for intelligence.
And the influence of that test, I mean, it's undeniable, isn't it?
Totally. It provided this tangible, although still heavily debated, benchmark for machine intelligence. It definitely framed a lot of that early optimism, giving researchers a concrete, if maybe flawed, target to aim for.
But it also seems like right from the start, it baked in this tension. Are we testing for real understanding or just a really convincing imitation?
And that tension became a foundational debate that honestly continues today. So while Turing laid that philosophical groundwork, you had others like John McCarthy, who, by the way, actually coined the term artificial intelligence at Dartmouth, starting to architect the practical system.
Okay, so McCarthy was more hands-on.
Very much so. He really spearheaded what we now call the symbolic AI approach. His work, like his 1960 paper, Recursive Functions of Symbolic Expressions and Their Computation by Machine, laid the critical groundwork for powerful symbolic programming languages, most notably LISP.
LISP, I've heard of that. So this symbolic approach, it wasn't about feeding machines tons of data like we do now with machine learning, right?
Yeah.
It was more about rules, logic.
Precisely. You've nailed it. Symbolic AI focused intensely on manipulating symbols, abstract representations of concepts or objects to represent knowledge and perform logical inference. deduction, reasoning.
Like programming and the laws of logic.
Kind of, yeah.
Yeah.
The core belief was that intelligence, in its very essence, could be entirely captured through these formal systems, almost like a grand mathematical equation or a meticulously defined set of rules. The idea was if you could just codify enough knowledge, facts about the world, relationships between things, logical operations, and provide the rules for manipulating that knowledge, then intelligence would just emerge.
And LASP helped make that possible.
LISP was revolutionary because it made it relatively easy to write programs that could manipulate other programs or symbolic expressions as data. This was crucial for building systems that could potentially modify themselves or reason about complex relationships symbolically.
Okay, that makes sense. So you had the symbolic logic-based approach from McCarthy. What other key visions were floating around then?
Well, complementing these logical efforts, you had Marvin Minsky, another giant in early AI research. Now, his hugely influential book, The Society of Mind, actually came much later, but his early work and thinking were already shaping how researchers conceptualized intelligence itself.
How did Minsky's vision fit in? Was it similar to McCarthy's?
It was different, focused more on the architecture of intelligence. Minsky advocated for an approach where intelligence wasn't this single monolithic thing, but instead it arose from the interaction of many simpler processes, or agents, as he later called them.
Like a committee in the head.
Exactly. Imagine this bustling society of mini minds inside your head, each one handling a specific, simple task, recognizing an edge, retrieving a memory, making a small decision. And it's their collective interaction, their communication and cooperation that produces what we perceive as complex thought or intelligent behavior.
That's a fascinating model.
It really is.
Yeah.
And this vision underscored that grand ambition. Let's try to reverse engineer human cognition. Let's break it down into these manageable, interconnected components that we could then potentially simulate or build in a machine.
So you've got Turing's challenge, McCarthy's logic, Minsky's architecture.
Yeah.
All these different threads seem to be pulling in a similar direction towards building thinking machines.
They absolutely were, and they kind of coalesced into this powerful, unifying idea that became really central to the Dartmouth generation.
Sure.
It became known as the physical symbol system hypothesis. By the mid-1950s, this idea had really solidified among these pioneers. It basically posited that a physical symbol system, essentially, a system like a computer that can manipulate symbols according to rules, was both sufficient and necessary for producing general intelligence.
Sufficient and necessary. Those are strong words. What do they really mean by that, and why was this hypothesis so absolutely central to their whole approach?
It's incredibly central, and yeah, those words carry a lot of weight. Let's break it down. First, necessary implied that any genuinely intelligent system, whether it's a human brain, an alien mind, or an AI, must fundamentally operate by manipulating symbols. Intelligence, in this view, inherently involves representing information symbolically and operating on those representations according to rules. You just can't have intelligence without symbol manipulation, they argued.
Okay, so symbol manipulation is a prerequisite for any intelligence. What about sufficient?
Sufficient was perhaps even bolder. It meant that if you could successfully build a system, a physical system that was capable of manipulating symbols in sophisticated enough ways, if you could give it a comprehensive enough set of symbols, rules, and a knowledge base, then that system would inevitably become intelligent.
Wow, so intelligence wasn't some mysterious spark or vital essence.
Exactly. It wasn't some ineffable quality. It was seen as an emergent property of complex enough symbol manipulation. This hypothesis gave early researchers what felt like a clear, albeit incredibly challenging, blueprint. Figure out how to abstract the world into symbols, define the right rules for manipulating them, build a machine that can do it fast enough, and boom, intelligence would emerge.
So that really defined AI as a subfield.
It fundamentally defined AI as, yes, a coherent subfield of computer science, explicitly dedicated to understanding and building these intelligent entities based on symbol manipulation. It was a powerful unifying vision. But, as we're about to see, it also perhaps boxed their thinking into a very specific computational paradigm, and, well, it carried within it the seeds of future challenges and some significant disappointments.
Okay, so armed with these grand visions, this unifying hypothesis, and this brand new, powerfully evocative name, artificial intelligence, the research started. AI took its very first tangible steps.
The work began in earnest.
And what's truly fascinating, almost immediately, is how quickly those early creations, even though they were relatively simple by today's standards, began to profoundly challenge how humans perceived what a machine could do or maybe even what it could be.
Yeah, the human reaction was almost as interesting as the technology itself.
And a perfect, maybe the most famous illustrative example of this is Joseph Weizenbaum's program ELIZA, which he developed at MIT in the mid-1960s.
Ah, yes, Eliza. The chatbot therapist.
Exactly. So ELIZA was a chatbot, but it's crucial to understand, as you mentioned earlier, it was a rules-based system. It did not use machine learning, right? There was no trading on vast data sets.
Zero machine learning. It was essentially a clever script, a set of pre-programmed rules and templates. Its main function was basically to paraphrase the user's own statements, often by just picking out keywords and reflecting them back as questions.
Can you give an example?
Sure. If you type something like, "I'm feeling quite worried about my job," Eliza might respond with something simple like, "Why do you say you're feeling quite worried about your job?" Or it might pick out job and ask, "Tell me more about your job." It was designed specifically to mimic a Rogerian psychotherapist who uses that technique of reflective listening to encourage the patient to talk more.
Okay, so fairly simple pattern matching and canned responses, essentially.
Fundamentally, yes. Cleverly done, but simple underneath.
And yet, here's where it gets really remarkable. Despite that underlying simplicity, the impact it had on the people who interacted with it was, as Weizenbaum himself later wrote, striking.
Understatement, maybe?
Right. Some people, even after really short interactions, became utterly convinced that Liza was human. Others started ascribing understanding and motivation to it. They formed emotional attachments, shared deep personal problems. Even after Weizenbaum explicitly told them how the program worked, we'd explain it was just rules, just tricks, and they'd say, "Yes, I understand, but," and continue confiding in it.
That's the truly astonishing part, isn't it? Knowing it's a program, but still feeling that connection, still attributing genuine intelligence and empathy.
It is, and Weizenbaum himself was deeply troubled by this. He observed, with some real dismay, that he had not realized that extremely short exposures to a relatively simple computer program could induce powerful delusional thinking in quite normal people.
Powerful delusional thinking. Strong words.
Very. And this phenomenon, our tendency to project intelligence and feeling onto machines, was later dubbed the ELIZA effect. It highlights this critical, enduring doubt or maybe observation that emerged right at the start of AI's history. We humans seem hardwired to overascribe intelligence.
We want to see understanding, empathy, motivation, even when it's not really there.
Exactly. We project it onto the machine. It blurs the lines between what's true cognition and what's just clever mimicry. It's a powerful reminder of our own psychological predisposition to find patterns, to find meaning, maybe even companionship, even where it doesn't truly exist in the way we might assume. It's a profound lesson in human perception versus technical reality, and it started way back then.
And that ELIZA effect, that tendency to project, it didn't just stay with simple chatbots, did it? It seems to underpin a broader phenomenon that shaped AI's whole history.
You're thinking of the AI effect.
Exactly, the AI effect. It's a fascinating connection to draw because the AI effect describes this powerful human tendency we have to, well, basically redefine whatever artificial intelligence achieves as not really being that hard after all once it's done.
Right. Once a machine can do it, suddenly it wasn't real intelligence in the first place.
Precisely. The goalposts for true intelligence get quietly, or sometimes not so quietly, moved. It's like, oh, okay, a computer can do that now. Well, that wasn't really intelligence anyway. Real intelligence is this other thing it still can't do.
It's a pattern we've seen play out again and again over the decades, haven't we? Chess is a classic example. For ages, chess was held up as this ultimate benchmark of human intellect, strategy, foresight.
The pinnacle of strategic thinking.
Right. Then, 1997 happens. IBM's Deep Blue supercomputer defeats Garry Kasparov, the reigning world chess champion. A huge, monumental achievement, a genuine watershed moment for AI. But what happened immediately after?
Almost instantly, many commentators started to dismiss the accomplishment's relevance to real-world cognition.
Oh.
The narrative shifted. Suddenly, chess was easy to represent mathematically. It had perfect information, a relatively finite, albeit huge, number of possible moves.
It was just a math problem.
Yeah, that was the argument. They called it just a fancy trick of math or brute force calculation, not genuine understanding or human-like intuition. The implication was clear. Okay, a machine solved chess, but that wasn't real intelligence because it was solvable by computation. The definition of intelligence just subtly shifted to something more elusive, something machines still couldn't do.
And this wasn't just about structured games like chess, was it? I remember critics confidently predicting that computers would, quote, never master the kinds of ambiguous natural language tasks needed for things like crossword puzzles.
Right, crosswords require broad general knowledge, understanding puns, wordplay, nuance.
Exactly. Or even competing effectively on a complex quiz show like Jeopardy, which involves parsing tricky questions, understanding context. These were seen as uniquely human domains, relying on fuzzy knowledge and intuition.
Definitely seen as beyond machines at the time. Yet, what actually happened?
Well, as our sources vividly recount, crosswords fell within 2 years of Deep Blue's victory. AI systems were developed that could solve them remarkably well.
They cracked the ambiguity faster than expected.
And then, less than 12 years after that, you had IBM's Watson going on Jeopardy, and just handily defeating Ken Jennings and Brad Rutter, the two greatest human players ever.
And Watson wasn't just recalling facts. It had to parse those complex, often pun-filled natural language questions, disambiguate meanings, search vast databases, integrate knowledge, and even buzz in with confidence. It was a stunning demonstration.
Absolutely. But again, after Watson, you heard whispers, well, that's impressive information retrieval, but is it thinking?
The goalposts moved again. Each time AI achieved something previously thought to be uniquely human, the definition of true intelligence seemed to morph, always staying just out of reach of the machines.
So what does this recurring AI effect really tell us? It feels like it reveals a deep-seated, maybe even philosophical tension in how we view artificial intelligence.
I think it's incredibly revealing on multiple levels. On one hand, the AI effect is a fantastic illustration of the continuous, sometimes genuinely astonishing progress of AI. Machines keep getting better. They consistently conquer tasks we once thought were impossible for them, things we reserved for human intellect. It's a testament to the ingenuity of the researchers.
Sure, it shows progress.
But on the other hand, it reflects this persistent, perhaps even fundamental skepticism, maybe even a bit of defensiveness, about whether machines can ever really achieve the broad, flexible, intuitive intelligence that we humans possess. This constant redefinition, this moving of the goalposts, it fuels those cycles where the bold optimism of the pioneers gives way to later disillusionment, or, as we've seen, just a redefinition of what intelligence actually means once a machine achieves it.
So it forces us to ask.
It forces us to ask, what is it that we truly consider intelligence? And why is that definition seemingly so fluid, so slippery, specifically when we're talking about AI? Does it actually tell us more about the limitations of machines? Or does it tell us more about our own definitions, our own biases, our own view of what makes us special? It's a profound question raised by this effect.
Okay, so we've seen how early AI, like ELIZA, triggered the ELIZA effect, our tendency to project intelligence, and how later achievements led to the AI effect, where we redefine intelligence. These are about human perception.
Right, how we react to AI.
But the early days of AI also saw the emergence of much deeper, more fundamental doubts. These weren't about perception. They were objections rooted in philosophy and the very nature of mathematics itself. They questioned inherent, maybe unyielding limits to what any formal computational system could ever achieve.
These were serious intellectual challenges coming from mathematicians and logicians looking at the core properties of computation. Building on groundbreaking work from the early 20th century, they began identifying fundamental limitations of what were called discrete state machines.
Which is basically what computers are, right? Operating on precise logical steps.
Exactly. And one of the most famous and frankly mind-bending results was Gödel's incompleteness theorem from 1931. Gödel showed that in any sufficiently powerful logical system, basically, any formal system complex enough to include basic arithmetic, you can formulate statements that are true, but which can neither be proved nor disproved within that system itself. Unless, that is, the system itself is inconsistent, which is obviously undesirable.
Okay, let me try and wrap my head around that. So within any powerful enough rule-based system, there are truths it simply can't reach through its own rules.
That's the essence of it. There are inherent limitations to what can be proven solely by manipulating symbols according to a fixed set of axioms and rules.
And that must have been a direct challenge to that symbolic AI approach we talked about, the one that believed intelligence could be entirely captured through formal rules and symbols.
A huge challenge. For those pioneers who embraced the physical symbol system hypothesis, the idea that symbol manipulation was sufficient for intelligence. Gödel's theorems represented this fundamental, seemingly unyielding wall. It suggested that no matter how complex or comprehensive you made your AI's rulebook, there would always be mathematical truths it couldn't deduce or problems it couldn't solve using only its internal logic. It put a hard theoretical limit on the ambition of creating an all-encompassing logical intelligence. It really chipped away at that sufficiency claim for some thinkers.
And Turing himself added to this.
He did. Alan Turing, building on his own work on computation, further solidified these theoretical limits in 1937 with his work on undecidability, particularly the halting problem. He essentially showed that there are certain things that such a machine cannot do. Specifically, there's no general algorithm that can determine for any given program and input whether that program will eventually stop or run forever.
So some questions are just fundamentally unanswerable by computation.
For certain classes of problems, yes. A machine attempting to answer might either give a wrong answer or fail to give an answer at all, just running indefinitely, regardless of how much time or processing power you give it. Again, this wasn't about technology not being good enough yet. It pointed to inherent logical barriers within computation itself.
This feels critical. It raises these really profound questions, doesn't it? About the potentially unbounded, maybe intuitive nature of human intellect versus the inherent formal limits of these rule-based systems. It suggests that if human thought is capable of insights beyond formal proof in certain ways, then maybe a machine operating purely on a finite set of rules could never fully replicate it.
Precisely. It opened up that possibility, and others echoed this. Norbert Wiener, a key figure in cybernetics, which was a related field exploring control and communication in animals and machines, also highlighted limitations. He noted that a logical machine following definite rules need never come to a conclusion.
It could just get stuck.
Yeah, it could get trapped in cycles, endlessly repeating steps, or it could just go on grinding through different stages without ever coming to a stop, never reaching a definitive answer. These weren't just abstract theoretical curiosities. They pointed to deep structural challenges for the very foundations of the symbolic AI dream. They hinted that maybe intelligence wasn't just symbol manipulation.
These foundational doubts, rooted in logic and math, really feel like they set the stage for later ongoing debates within AI, like the tension between really understanding how AI works versus just getting it to work, regardless of explanation.
Definitely. This connects directly to more modern debates, like what became known somewhat controversially as the alchemy debate. This division became particularly sharp with the rise of deep learning.
Because deep learning often produces amazing results, but we don't always know exactly how it gets there, right? The black box problem.
Exactly. Deep neural networks can learn incredibly complex patterns from data, but interpreting the internal workings, the reasoning behind their decisions can be extremely difficult, sometimes impossible. And this led to some sharp critiques.
Like Ali Rahimi's.
Right. Ali Rahimi, in a pretty provocative 2017 conference address, famously compared many current deep learning methods to alchemy.
Alchemy, like trying to turn lead into gold without understanding chemistry.
That was precisely his analogy. He argued forcefully that the field desperately needed rigorous, reliable, verifiable knowledge about why these systems work, not just demonstrations that they do work impressively on certain tasks. His concern was profound, especially, as he put it, for systems governing healthcare and our participation in civil debate.
Because if you don't understand how it works,
how can you possibly trust it with critical, life-altering decisions? How can you debug it when it fails? How can you prove its safety, ensure fairness, or guarantee it won't behave unpredictably in new situations? He was calling for a return to more rigorous scientific understanding, moving beyond just impressive empirical results.
That's a really powerful critique, especially given the stakes.
Yeah.
But there was pushback, wasn't there, from people actually building these systems?
Oh, absolutely. Figures like Yann LeCun, who's the chief AI scientist at Meta, formerly Facebook, and a pioneer of deep learning, offered a strong counterargument. LeCun contended, quite persuasively for many, that engineering artifacts have almost always preceded the theoretical understanding.
He gave examples.
Yes, he pointed to history. The telescope was invented and used long before we had a complete theory of optics. The steam engine revolutionized industry well before the laws of thermodynamics were fully formulated. The airplane flew before we had a perfect grasp of aerodynamics.
So build it first, understand it later.
That was his point. For Lacan and others in this camp, the priority should be on inventing new methods, new techniques, and yes, new tricks, pushing the boundaries of what's possible, even if the deep theoretical understanding lags behind. The engineering often drives the science, not the other way around.
So this represents a really profound philosophical divide within the field itself.
It absolutely does.
Yeah.
Are we aiming for deep theoretical comprehension of intelligence, a fundamental understanding of why AI works? Or are we primarily focused on building useful, practical, albeit sometimes inexplicable, breakthroughs that achieve results in the real world? It's a fundamental tension. Understanding versus utility. Both sides have valid points, and the balance between them constantly shapes research priorities and funding.
And alongside these debates about understanding, as AI systems became more capable and started moving out of the lab and into the real world, another layer of doubt, or perhaps caution, emerged the shadow of AI snake oil.
Right. This isn't just about a lack of understanding, it's about active misrepresentation and hype, and the very real consequences that follow.
So what exactly is AI snake oil?
Yeah.
How do our sources define it?
AI snake oil is the term used to describe situations where AI works to some extent, but is accompanied by exaggerated claims by the company selling it. Our sources really emphasize that the boundaries between what an AI system can actually reliably do and what it's claimed it can do are often a bit fuzzy, and sometimes that fuzziness is deliberate marketing spin.
Selling the sizzle, not just the steak.
Pretty much. And this hype, this gap between promise and reality, leads to very real and sometimes quite severe consequences for individuals and for society as a whole.
What's one of the biggest consequences highlighted?
One of the most significant is over-reliance. This is where AI systems are used as a replacement for human expertise instead of as a way to augment it. People start trusting the AI beyond its actual capabilities because of the hype.
Can you give us a more concrete example of what that over-reliance looks like in practice, beyond just a general sense of risk?
Certainly, let's take an example from healthcare, a critical area. One source discusses a study evaluating an AI system designed to detect sepsis, a really dangerous, life-threatening condition in hospital patients. Now, the system worked in the narrow sense that it did identify some sepsis cases based on patterns in patient data.
Okay, so it had some success.
Yes, but it also had a high false positive rate and a significant false negative rate. This meant it both missed actual sepsis cases, potentially delaying life-saving treatment, and it raised numerous unnecessary alerts for patients who weren't septic.
Creating noise and potential danger.
Exactly. The study calculated that for clinicians to properly evaluate every single alert generated by this AI, they would have to perform 109 detailed evaluations just to find one actual case of sepsis that might have been missed otherwise.
Wow, that's not helpful augmentation.
Not at all. That's creating a massive new burden, a recipe for alert fatigue where busy staff start ignoring all alerts, including potentially valid ones. It undermines trust, misallocates precious clinical resources, and could actually lead to worse outcomes despite the AI working according to its algorithm. It's a classic case of over-reliance driven by hype, creating more problems than it solves.
So the AI is functioning as programmed, but its application in the real world, fueled by exaggerated claims, is counterproductive or even harmful.
Precisely. And it's absolutely crucial to understand that even when AI works well, meaning it functions exactly as its designers intended, without bugs or statistical flaws, it can still be harmful depending on its application.
How so?
Facial recognition technology is a prime example often cited. Even if a system is highly accurate at identifying faces, its use can still be deeply problematic. We've seen it abused for mass surveillance by governments, used in ways that disproportionately affect certain communities, or deployed in contexts that erode privacy and civil liberties.
So the tech itself might be working, but the way it's used is the problem.
Exactly. The harm isn't necessarily coming from AI failure or overhype in this case, but from the AI working exactly as intended within a flawed, unethical, or malicious framework. This forces us to think beyond just accuracy or capability and introduces these crucial harm and truthfulness axes for evaluating AI systems. We have to ask, is it accurate? Is it truthful in its claims? And fundamentally, is it harmful in its real-world impact, even if it's working perfectly? The earliest doubts about true capability and the risks of projecting intelligence have now morphed into these very concrete ethical and societal challenges we're grappling with daily.
Okay, so we've traced the early optimism, the emergence of fundamental doubts from math and philosophy, the cycles of hype and the AI effect, and the dangers of snake oil. It sounds like a field constantly grappling with its own promises and limitations.
It really has been a roller coaster, yeah.
But despite all these deep divisions, those foundational limitations identified early on in the periodic AI winters where funding dried up, it seems like those audacious dreams of the AI pioneers never truly faded away.
No, they persisted. The core goal remained.
And in fact, in recent years, we've witnessed this powerful resurgence of capabilities. It feels undeniable, particularly with the incredible advancements in deep learning, and now, even more recently, large language models. It feels like we're living through another major AI boom, doesn't it? Almost echoing the optimism of Dartmouth, but maybe on steroids.
We absolutely are. There's been a dramatic acceleration. By the mid-2010s, deep neural networks really hit their stride. They became the approach of choice for a huge range of applications, especially perception tasks. They demonstrated that for things like image recognition or speech understanding, no other known technique can compete with deep neural networks.
We saw this with things like ImageNet.
Exactly. The ImageNet challenge results were a major turning point, revolutionizing computer vision. And we saw similar breakthroughs in speech recognition, powering the voice assistants many of us use daily. These networks, with their dozens or even hundreds of layers, trained on absolutely massive data sets, started cracking problems that had completely stymied those earlier symbolic AI approaches for decades. It really was a paradigm shift that overcame many previous roadblocks.
And now, of course, we're completely immersed in the age of large language models, LLMs,
Right.
systems like OpenAI's ChatGPT, Google's Gemini, Anthropic's Claude. These feel like a whole new frontier again.
They really do represent another significant leap.
And the capabilities they display are just, well, stunningly impressive.
Yeah.
Almost beyond what many people, even AI researchers, thought possible just 5 or 10 years ago.
They are indeed, and the sheer breadth of their capabilities is what's often so astounding. These models can, as our sources point out, do things like write witty limericks, which requires creativity and language understanding. They can solve reasoning puzzles that require you to think around corners, problems involving common sense or analogical thinking that were historically very hard for AI.
They can code too, right?
Yeah, remarkably well. They can often write much better code than many moderately experienced human programmers, completing complex coding tasks, finding bugs, translating between languages. It's quite efficient. But perhaps the most striking aspect, the one that really gives them their power, is their collective knowledge.
You mean their ability to synthesize information from the colossal amounts of text data they're trained on?
Exactly that. Geoffrey Hinton, often called the godfather of AI for his pioneering work on neural networks. He noted this back in May 2023. He said these systems collectively knows more about the world than any one single human who has ever lived, which is a staggering claim.
How did he explain that?
He used this great analogy. He said it's as if you had 10,000 people, and whenever one person learned something, everybody else automatically knew it. It's this instantly shared, massively distributed knowledge, gleaned from processing trillions of words, that gives LLMs their extraordinary ability to converse coherently, generate informative text, and answer questions on almost any topic you can throw at them. They're drawing from this vast, eclectic digital library internalized during training.
Okay, that's an incredible capability. However,
Sure.
despite all this prowess, all this knowledge, does that ELIZA effect we talked about earlier still apply, perhaps even more strongly now?
I think it absolutely does, and maybe it's even more potent. Interacting with these highly fluent, knowledgeable LLMs, as one of our sources notes, definitely yields the illusion that one is interacting with a cognitive agent. It feels like there's understanding, intention, maybe even personality, but the source continues, it's an illusion nonetheless.
So the illusion of intelligence is just much more sophisticated now. More convincing, but still fundamentally an illusion.
That's the critical distinction experts keep trying to make. These models are, at their core, extremely complex mathematical models and computer programs. They operate by performing sophisticated statistical calculations, multiplying together large matrices of numbers, as one source puts it, essentially predicting the next most probable word or token in a sequence based on the patterns learned from their training data.
So it's pattern matching on a massive scale.
An incredibly sophisticated form of pattern matching and generation, yes. But they don't possess genuine understanding, consciousness, sentience, beliefs, or a lived experience in the way a human does. The illusion they create, while incredibly compelling and often very useful, is ultimately a product of their sophisticated mimicry and statistical prowess, not genuine cognition or feeling.
And this compelling illusion is further complicated by something else you mentioned, the training data itself. LLMs learn from the web, basically.
Vast swaths of the internet, yeah. Human conversations, writings, code.
Which means, as our sources highlight, that human biases, our prejudices, stereotypes, blind spots inevitably get embedded within these models during training. This isn't just a minor technical glitch that can be easily fixed, is it?
Not at all. It's a fundamental consequence of how they're built and trained right now. The training data itself is often, as one source describes it, an odd slice of human data. It's predominantly text from the internet, heavily skewed towards content generated in certain languages, mostly English, from certain cultures, often Western, particularly American, reflecting the perspectives and priorities of those who created the data sets primarily American and generally English-speaking AI firms decided to gather it.
So the AI learns a skewed view of the world.
It inevitably does. This results in models that can amplify certain viewpoints while marginalizing others, perpetuate harmful stereotypes, and generate outputs that lack fairness or representational accuracy for a global audience. It raises really critical questions about whose narratives get privileged, whose biases become encoded as knowledge, and how this impacts the information these incredibly powerful models disseminate. They essentially hold up a mirror to the internet, biases and all, which is often a problematic reflection of humanity.
Okay, so even with these incredible capabilities, we still face lesions of understanding and embedded biases. This brings us back then to that ultimate, still unresolved quest that motivated the Dartmouth pioneers, and one that remains very much alive, maybe more debated than ever today: artificial general intelligence, AGI.
The grand goal.
The enduring dream of achieving truly human-level, flexible, adaptable intelligence in a machine. Not just good at specific tasks, but generally intelligent like us. Where does that stand now?
Well, it's definitely considered a serious possibility we should take seriously. The mainstream debate among AI researchers has largely shifted from if AGI is possible in principle to more practical questions like when we might reach it, what it will look like, and perhaps most importantly, what we can do now to steer it in a more beneficial direction.
So it's seen as plausible, maybe even likely by some.
By many, yes. Though timelines vary wildly, from a few years to many decades or never. And it might not be a sudden switch. One perspective highlighted in our sources is that the history of AI actually reveals a gradual increase in generality over time, rather than a sharp, clear separation between narrow AI and general AI. Each major breakthrough, from symbolic systems to deep learning to LMs, has pushed the boundaries, making AI capable of handling a wider range of tasks in a more flexible way. It might be more of a continuum.
And this idea of gradual, maybe exponential progress leads some people, like the futurist Ray Kurzweil, to envision a future where humans actually merge with AI.
Kurzweil is definitely a prominent voice representing that enduring, bold optimism, maybe even more extreme than at Dartmouth, amplified by observing the exponential pace of technological change, particularly Moore's law in computing.
What are some of his predictions?
He makes some truly startling predictions. For example, he envisions that by the 2030s, so not that far off, we'll have technologies like medical nanorobots. These would be microscopic devices circulating in our bodies. And crucially, he predicts these nanobots could connect the top layers of our neocortex to the cloud.
Connect our brains directly to the internet.
Essentially, yes, allowing for what he calls indefinitely expanded cognitive power. Imagine being able to access vast databases instantly with a thought, communicate telepathically via the cloud, enhance your memory, your processing speed. It's a vision of a direct, seamless integration of human biological intelligence and artificial intelligence. It taps into that fundamental human desire for enhancement, for overcoming our biological limitations.
That's a lot to take in. A truly radical vision of the future. But with these grand visions, whether it's standalone AGI or this kind of human-AI convergence, come equally immense challenges, particularly the problem of control, or what the field calls alignment.
The alignment problem, yes. Ensuring that these increasingly powerful AI systems, especially potential superintelligences, truly serve human interests and values and don't inadvertently or intentionally cause harm. It's arguably the central challenge for the future of AI safety.
And how is that challenge viewed? Is the main fear AI going rogue, like in the movies?
That's part of the long-term discussion, the existential risks scenario. But our sources make a really crucial distinction for the nearer term. The biggest risks to humanity will arise from people misusing AI, not from AI going rogue in some kind of conscious Skynet-like rebellion.
Ah, okay, so the immediate threat is human misuse. not machine malice.
That's the more pressing concern for many researchers and policymakers right now. While the theoretical possibility of uncontrollable superintelligence is debated, the immediate tangible threat comes from intentional misuse by bad actors, criminals, terrorists, authoritarian states, or unintentional negative consequences arising from poorly designed or deployed systems, or systems whose goals aren't properly aligned with complex human values. It's really about how we humans choose to wield this incredible power.
That's a subtle but incredibly important shift in focus. It's less about the AI suddenly developing evil intent and more about humans using powerful AI tools for dangerous or harmful ends. Can you elaborate on how current alignment efforts try to tackle this and where the vulnerabilities might still lie?
Sure. Take current efforts to align consumer-facing chatbots like ChatGPT or Claude. The developers invest enormous effort in making them safer. These alignment techniques, things like reinforcement learning from human feedback, RLHF, are actually extremely effective at preventing chatbots from spewing toxic text or readily generating harmful, illegal, or unethical content for the average user asking straightforward questions. They put up guardrails.
So the safety measures work for casual use.
They're generally quite effective for that, yes. However, those same alignment efforts and guardrails often do little against adversaries. Determined individuals or groups, sometimes using automated techniques or cleverly engineered jailbreak prompts, can often find ways to bypass these safeguards and coax the models into generating dangerous or forbidden content, things like instructions for building weapons, generating sophisticated phishing scams, or creating large volumes of misinformation.
So the defenses aren't foolproof against determined attackers.
Not yet, no. It's an ongoing cat and mouse game. This means the challenges aren't just about building smarter and more capable machines. They're fundamentally about building responsible and robustly safe machines, designing effective and hard-to-circumvent safeguards, anticipating potential misuses, and critically, establishing norms, regulations, and ethical frameworks for how humans develop and deploy these increasingly powerful tools. The early dreams of thinking machines and the early doubts about their limits and risks are still very much with us, just amplified and transformed by the incredible capabilities and the inherent dangers of the systems we're building today. Hashtag outro.
Wow. Okay. What an absolutely expansive journey we've taken today. From that electrifying moment back in 1956 when artificial intelligence first got its name, a name that really captured this boundless optimism, didn't it? Igniting dreams of truly thinking machines.
It really set the tone.
And then we traced those first attempts, seeing how systems like ELIZA, even in their relative simplicity, starkly exposed our human susceptibility to what Joseph Weissenbaum called that powerful delusional thinking. Our tendency to see mind where there wasn't one.
The ELIZA effect, yeah.
Yeah.
A really early warning sign about human psychology meeting machines.
Then we explored how the AI effect has just continuously redefined what we even count as real intelligence, constantly moving the goalposts with every new breakthrough, always challenging our perception of what machines are capable of versus what true intelligence means.
Keeping intelligence always just out of reach, it seems.
Right. And we also touched on those deep philosophical and mathematical doubts, identifying those fundamental limits from Gödel and Turing that challenged the very notion of what rule-based machines could truly achieve, long before today's neural networks even existed.
Doubts that maybe got swept aside for a while but are still relevant.
Absolutely. So that core tension, then this push and pull between the audacious promise of human-level AI and the reality of the underlying mechanisms, the ethical nightmares, the potential for snake oil and hype. It feels like it's been there right from the start, and it's persisted throughout AI's entire history.
It really has been the defining dynamic of the field, hasn't it? Promise versus peril, capability versus consequence.
And modern AI, with its just incredible advancements in deep learning and these large language models we're all interacting with now, seems to embody both sides of that coin perfectly. It's a stunning realization of some of those bold early dreams, and yet, paradoxically, it's also amplifying those initial profound doubts and concerns.
It brings it all into much sharper focus, maybe higher stakes.
Which leaves us with a pretty provocative thought to end on, doesn't it? As these AI systems become ever more powerful, more pervasive, woven into pretty much every aspect of our lives now, from diagnosing diseases to writing poetry, are we, the human users, the observers, the citizens, are we actually getting any better at discerning genuine understanding from incredibly sophisticated mimicry?
Have we learned the lessons from ELIZA, from Deep Blue, from Watson? Or are we just as susceptible, maybe even more so now that the mimicry is so much better?
Exactly. Or, in our understandable haste and excitement to embrace the next breakthrough, the next amazing capability, Are we maybe just setting ourselves up for a much grander, much more impactful ELIZA effect on a societal scale?
Yeah.
Continuously projecting intentions, understanding, maybe even consciousness onto these mathematical models that are simply working as they were programmed to, whether for good or for ill, without us truly grasping their fundamental nature.
It's a critical question.
It really is. Those initial dreams and those initial doubts from AI's birth, they continue to echo today louder than ever, urging us, maybe demanding us, to question not just what AI can do, but what it truly is and what that ultimately means for us, the people living alongside it every single day.